So how to prove this? We draw a picture. Here is D. Okay. We take a rectangle to contain D because we are discussing the integration of f over D. This is always described using a rectangle containing D. Okay. Therefore, as usual, we take rectangle I containing D. That is the rectangle I. Then, by definition, FD, the zero extension of F, is integrable over the rectangle I. Okay. Therefore, given epsilon positive, we can find a partition of the rectangle I, denoted by capital P, such that the difference of the upper sum with respect to this partition and the lower sum of FD with respect to this partition is less than epsilon. This is the equivalent condition for integrability of functions over rectangle. Okay, so the partition, we draw the partition here. This is the partition of the rectangle. Okay. Now for the, maybe I will, yes, for the sub-rectangle of this partition, for a sub-rectangle in this partition, we have two cases. This is an n-dimensional sub-rectangle. Then J Cartesian product which the infiniment of the zero extension over this over J and the supplement of the zero extension FD over the rectangle J. This is an n-dimensional rectangle Cartesian product which is an interval. This gives us an n+1 dimensional rectangle. This is a rectangle in one more dimensional space, Rn+1. Okay, this is easy. An n-dimensional rectangle Cartesian product which is an interval. The result is an n+1 dimensional rectangle. Okay, now we will prove that the graph of the function is contained in the all such n+1 dimensional rectangle. Now we will prove this result. Okay, we will prove this result. If this is proved, then the this n+1 dimensional rectangle, the union of such n+1 dimensional rectangle covers the graph of F, and the total volume of such rectangle, the total volume of n+1 dimensional volume of such rectangle is precisely because the volume of a rectangle is the multiplication of the length of all its edges. So the first n edge is the edge of J. So the multiplication of the first n edge of this n+1 dimensional rectangle is the multiplication of all the edges of J. Therefore, this is the volume of J, n-dimensional volume, because J is n-dimensional rectangle. Then multiply the length of the last edge, that is capital Mj minus small mj. So this is precisely the color. This is precisely J capital Mj minus small mj, then a dimensional volume of J. So this is obviously the difference of the upper sum and the lower sum of our f. This is by the integrability of fd. Because the capital Mj and the small mj is computed using fd. Therefore, this is the upper sum of fd, subtract the lower sum of fd. So by the integrability of fd, this is less than epsilon. So we have proved that this finitely many n+1 dimensional rectangle covers the graph of f. The total volume of such rectangle is less than epsilon. If we can prove that they cover the graph of f, if we can prove that it covers the graph of f, then by definition, the graph of f can be covered by finitely many n+1 dimensional rectangle whose total volume is less than epsilon. So by definition, the graph of f has Jordan content 0, and the theorem is proved. Okay. So to prove this inclusion, we take a point in the graph AFA in the graph. So then by the definition of a graph, this means A belongs to D. Okay, A belongs to D, but D is a subset of the rectangle I. So A is a point in I. A can be here or A can be here. Okay. In fact, because AFA is from the graph of F, so the A must be in D. A in D, A could not be outside here, but A is here or A is here. Anyway, A belongs to a subrectangle J. There exists a subrectangle J such that A belongs to J. So A belongs to J, then and we also have MJFD. I have no place to write. Maybe I don't know whether I should go to next page. Okay, I go to next page. So I'm sorry, there's no picture here. So to prove that, so we take AFA from the graph, then A contained in D, and D is a subset of I. Therefore, there is a subrectangle J from the partition such that NJFD will not greater than FDA. FDA is FA. Why this inequality is true? Because MJ is the infiniment of FD over the rectangle J. Okay, but A is a point in J. A belongs to D. D is a subset of I. Therefore, there is some J such that A belongs to J. Because I is precisely the union of all the J, all the subrectangle J. Therefore, we have a J in D such that A belongs to J. Then A belongs to J means that the infiniment of FD over J will not greater than FDA. But because A is in D, therefore FDA is precisely FA. And this will not greater than capital NJFD. So this implies that AFA belongs to, since A belongs to J, and FA belongs to the interval small mg and capital Mg. So this proves that this inclusion is true. Okay, the inclusion we want is verified. So this theorem is completely proved. Okay. Now, so we have introduced the concept of Jordan domain. Jordan domain. And we know that a function is integrable over a Jordan domain if the point of discontinuity is Jordan content 0. Jordan content 0. Okay, so this is very important. So our integration theory almost established. Using integral, we can talk about the volume of a general subset of Rn. Okay, we know how to compute, how to define the volume of a rectangle. We know the volume of a rectangle, which is the product multiplication of all its edges. Okay, but for general subset, how to define the volume? Using integral, this is a very easy task. So we have the definition. Suppose D is a bounded subset in Rn. And so the constant function whose value at every point is 1. Such a function is continuous. Maybe I make a mistake. Sorry, not this. So we have a constant function. The constant function is denoted by 1. Defined on D. The value of every point is 1. Okay, for any x in D. Now, how about the general extension of this constant function? So this is D. Its general extension is such a function. By our notation, denoted by 1D, which is a function defined in Rn, which is the value of this function is 1 if x belongs to D, otherwise 0. Okay, so this function, how about the discontinuity of this function? It is easy to see that those points where this general extension is not continuous is precisely the boundary of D. It is easy to prove that the discontinuity of the general extension of the constant function 1 is precisely the boundary of D. Therefore, this function is integrable if and only if the boundary of D has Jordan content 0. That is, D is a Jordan domain. So that is the constant function. Our discussion here tells us that the constant function is integrable over D if and only if D is Jordan domain. Okay, now therefore we can define the volume of D to be the integral of the constant function 1. Okay, so this extends the definition of volume. Previously we can only compute the volume of rectangles. Now for using the integration for every subset, the general subset, we can talk about whether it has a volume. So we know that if it is a Jordan domain, that it has a volume. What's the volume? The volume is precisely the integral of the constant function 1 over the domain.